introduce the speaker today, Davide Ferri from University of Torino and VUB. He's going to talk about from sets to quivers, oidification and the Yang-Baxter equation. Please go ahead.
Thank you very much, and thank you everybody for being here. So the topic of my talk would be, quivers and this philosophy of oidification and how it is related to the Yang-Baxter equation. So it's kind of hard to put all these things together in a cohesive talk. So I tried to stick to the following rules. I will delve a little bit less into my own original results and more on the background theory when it comes to the Yang-Baxter equation part and some new ideas, but a little bit less formalized when it comes to the oidification part and the use of quivers. Why this? Well, first, because maybe some of you will be less familiar with the field, so it's better to have more of an overview of the entire research field without spending so much time on the very specific research of a very specific random PhD student, which I am. And especially because I've seen that you will have more talks from people who are in the Yang-Baxter community in the next months. I think next one will be Carsten Lietzel in 1 month, then you will have Rong Tang in a couple of months. So I think this talk can also function as a little bit of an introduction to some topics that you will see again. I will start with the definition of quivers. So what is a quiver for me? It's basically a directed graph with loops and with possibly multiple arrows between two vertices. So I take a set of arrows, Q1, a set of vertices, Q0, and a source and target map. Why do we call them quivers? This was introduced by Gabriel in 1972, and why don't we call them just directed graphs? Well, because there are already too many notions of graphs that are conflicting with each other. And basically, when you see the term quiver, it's kind of flagging that you're doing more algebra than topology or combinatorics. It's like we're doing algebra here. In the words of Jonathan Smith, graph theory is more of a notation than a theory. So being a notation, it's kind of important to see, since this is a language, are we talking about something relevant or not? So it's important to see what this language is talking about. And this is what I will present in the first part of my talk. So a usual philosophy in mathematics is when I introduce something, I also have to give you the notion of the morphisms between these things. And here is where most of the match is played, because there are two notions of morphisms for quivers. One that is the most general one. So a morphism of quivers between Q and R is a pair of maps between the arrows and between the vertices. And these maps makes these two squares commute with respect to the source and the target. And then I have the notion of a strong morphism. So when Q and R are two quivers over the same set of vertices lambda, a strong morphism over lambda is a morphism of quivers whose vertex component is the identity. I call quiv and quiv lambda the two respective categories defined by quivers with two respective notions of morphisms. If you want a graphic idea, so a morphism is something that takes an arrow into another arrow, that takes the vertices into vertices, and it sort of respects the whole thing. A strong morphism is much more restrictive. It doesn't touch the vertices at all. It just moves the arrows, and it may look like a lot restrictive. And indeed, one thing that we cannot do with strong morphism, for instance, is identifying vertices with each other. Sort of an idea of quotients, which is something we would like to do. But I will explain how they are useful. The category of quivers over lambda with strong morphisms is a monoidal category. So this was defined by Ryoko Kenji Matsumoto and Kenichi Shimizu some time ago. Basically, they noticed that you can take the quiver of all composable pairs of arrows where the first one lies in Q and the second one lies in R. It is this picture here. This is sort of a quiver of paths, and this is defined as the tensor product of Q and R. And the monoidal unit is the loop bundle with one loop on each object. This is a monoidal category. when Q and R are the same quiver, Q tensor Q is just a set of length 2 paths over Q, which is also interesting to bear in mind. And this brings us back to the first question. So why are we studying quivers? Okay, this all comes from the theory of partial algebraic structures. If you have an operation, an n-ary operation on a set, you can have a partial algebraic structure, a partial n-ary operation, if it's just defined on a subset of a to the n, not the whole of a to the n. So, for instance, when you have a quiver, it is natural to define binary operations not on q1 times q1 to q1, but as morphisms q tensor q to q. And this is naturally a partial structure on the set of arrows, where the only pairs of arrows on which the operation is defined are the consecutive pairs. We will go back into this in a moment, but what I want you to observe is that the set of definitions of a partial binary operation is always a relation on the set. So it's natural to ask what sort of properties this relation satisfies. A very first one that comes to mind is defunctionality. So what is a defunctional relation? It's a relation that basically, just look at this picture. You have your set X. In this picture, the set has 6 elements, and X times X is just a 6 by 6 square. And the elements of the product that belong to the relation S are shaded in gray. And being defunctional basically means that whenever you have 3 vertices of a rectangle, you also have the 4th one. The relation of consecutive arrows in a quiver is always defunctional, because if X is in relation with Z2, Z1 is in relation with Z2, this means that the source and target here agree. So if Z1 is also in relation with Y, X is indeed in a relation with Y. What is not trivial to see, but also not incredibly difficult to see, is that every defunctional relation on a set is the relation of consecutive arrows of a quiver for a suitable quiver structure on the set. By the way, I want you to know that I have discussed this in front of a blackboard with Marino Gran, who is a category theorist you may know. We have been discussing about this for a couple of hours, and we came to a couple of conclusions on this construction. First, that quiv lambda is monoidal really on any category C when you take internal quivers in a category, which you can imagine is something you can do as long as C has finite limits. However, this equivalence doesn't really hold in any category C, so we are really using some properties of set here, so you should categorize the proof and pin down what properties of sets you're using, which I haven't done, so I have no idea how this works. I just know that it works in set and it doesn't work in general. And it's definitely a story for another time. But this basically means that quivers and defunctional relations are sort of the same thing. So quivers are good to discuss partial structures whose domain of definition is a defunctional relation, which is something we may want. For instance, when we require this partial operation to have an associativity property, for instance. So let's give you a concrete example. If we have this defunctional relation on a set of 6 elements, this is exactly the relation of consecutive arrows of this quiver down here that you can reconstruct by hand. Okay, oidification. It is a terrible name, I haven't chosen it. And it comes from the fact that when you take the oidified version of something, you usually add the suffix oid to the name. What does it mean? Many people will say, oh yes, oidification, so making partial things. In my mind, it's more like taking quiver theoretic versions of set theoretic things, which is taking many vertices versions of one vertex notions. Sets become quivers, for instance. Monoids become small categories, or if you don't care about being small, just think about categories. Groups become groupoids, small again. Algebras become algebroids and so on. And as we have seen, this philosophy make you shift between the total and partial, but also between the set and quiver. And I also have to tell you that this philosophy of oidifying algebraic structures is not mechanical. We don't have an algorithm to do this. We don't have a theoretical framework that just gives us the oidified versions of things. Not all notions admit an oidification, apparently, and some of them seem to admit more than one sensible oidification. There are 2 or 3 notions of algebroids that don't really coincide, for instance. And there is also a notion of Hopfish algebras that I think also aims at being an oidification of algebras, for instance. So there are some concepts that don't oidify necessarily in just one way. Again, why are we oidifying things? Why are we working on quivers? Let's start with a short story. In a moment, I will explain to you what the Yang-Baxter equation is. But before, I want you to know that some things called solutions to the Yang-Baxter equation, which are some algebraic things, have been an object of investigation for some time, and some people have tried to classify them. And one of the most efficient algorithms to do this was found by Daimi van Goudenberg, and then it became a paper with van Goudenberg, Bogaerts, and Vendramin in 2025. Van Goudenberg was doing her master thesis back then. I think now she is a PhD student in the KU Leuven. And her idea of classifying these algebraic structures was taking undefined things, so indeterminate structures, where the outcome of an operation can be multiple things, and then trying to restrict the range as much as possible until it became singletons. And when you have singletons, you have a precise value for the operation. She was using something that is called partial cycle sets. They are not really partial structures, but rather they are hyperstructures, which is sort of dual to partial structures. But partial structures, as I said, are sort of the dual approach to hyper. And you can try to computationally construct things in the dual way, in a very similar way. So you take something that is partial and you try to globalize it forcibly as far as you can. And when you have globalized it, so when you have reduced the set of vertices of your quiver to one single vertex, you have a total structure. This is a computational way of producing stuff. Unlike hyperstructures that are not very well studied, partial structures have a lot of theory behind them. The language of quivers is studied a lot, and the language of partial actions of groups and globalizations is also studied a lot. You can see a paper of my colleague Paolo Saracco and collaborators who did this on partial actions of groups, and it's a very nice paper. I don't remember all the authors, I'm sorry, but he was one of those. And third reason, there are indeed mathematical behaviors that are better described by partial structures rather than global ones. And if you want an everyday example, categories. Categories are partial monoids. And many things that you see in category theory are things in partial algebra. Say, for instance, what is a least common multiple in a partial monoid? You do this all the time in category theory, but you call it push out or pull back. It's just a least common multiple. So I want to apply this partial viewpoint, which is also a quiver theoretic viewpoint of oidification, to the world of the Yang-Baxter equation. And before doing this, I want to introduce what the Yang-Baxter equation is, and I want to give a little bit more of known theory rather than staying a lot on my own results. And I want to start with an in memoriam, because last year Professor Yang from the Yang-Baxter equation indeed passed away in October. As you may know, he was one of the most influential physicists of the last century, and he did really a lot of things. If you see on his Google Scholar, the first 3 papers you will find are these ones. The first one is maybe sounds a little bit obscure to you, conservation of the isotopic spin and so on, but if you see the others, maybe this clarifies it a bit. Yes, this is the same Yang as the Yang-Mills theory. The second paper is question of parity conservation in weak interactions, which also sounds obscure, but basically in 2005, so when he was more than 90 years old, he was able to prove that our universe is not symmetric under left-right symmetry, which is like the same as North Pole, South Pole in magnetic fields. In the words of Richard Feynman, this is like looking at a magnet and seeing that there are hairs growing on the South Pole, say. This is mind-blowing. It's one of the greatest results of physics in the last century. It's completely out of the blue. Then you have the Ising model, also from Yang, and only fourth in the list, but still with more than 3,000 citations, you have this paper from 1967 where he introduces the Yang-Baxter equation. Just to let you know that the guy got a Nobel Prize in physics for reasons, like he did a lot. And this is the paper, and this is the Yang-Baxter equation in slightly different form. What is this paper about? Okay, so Yang here was trying to solve an n-body problem, which is known to be a very difficult problem. If you know some celestial mechanics, n-body problem is non-integrable and it's super wild. So much that it actually inspired works of fictions like the book you see here and that I've read, and it's very nice. But he's doing an n-body problem in the quantum realm, and he's doing it one-dimensional. So we have 1 degree of freedom. Of course, these are not particles, these are wave functions because we're in quantum mechanics, but don't worry, I will just give you a rough idea of what's going on. So you have these n particles on a line. It's a simplification. And these particles move in time. And at some point, they interact with each other. They will go past each other. And this interaction, for whatever reason, is governed by a tensor of type 2,2, which is exactly what you see here in the Yang-Baxter equation. So the Yang-Baxter equation is a compatibility on the interactions of these particles. These particles will keep moving and moving and moving. And the Yang-Baxter equation can be interpreted as a compatibility on the interaction of this form. And if it looks familiar to you, it's because this is the third Reidemeister move, which you may have seen in knot theory. And when this compatibility holds, you know that the system is integrable. So this is the Yang-Baxter equation. And why is it called Yang-Baxter? Well, because nicely, Rodney-Baxter retrieved the same equation from a completely different viewpoint in statistical mechanics, studying an 8-vertex model. By the way, this is also an in memoriam because Rodney-Baxter also passed away last year, which, by the way, is a little bit of a high responsibility to people in my field now trying to continue this legacy, because we lost both of them. And I don't want to go into 8-vertex models and that stuff, but there is a lot going on here too, and I encourage you to read the literature if you like this sort of things. I will give you the mathematical framework we're working with, which is the following. So I will give you what a solution of the Yang-Baxter equation is in any monoidal category. You have an object and a morphism from B tensor V to V tensor V, such that this braid-like relation holds in the endomorphisms of V tensor V. If the category is not strict, put associators whenever you don't see them. For me, all monoidal categories will be strict because it's easier, but just put associators if you like it. Why was the set-theoretic Yang-Baxter equation introduced? Well, because Drinfeld at some point wanted to produce solutions in VEC, which are the solutions interesting to physicists. So he was trying to take solutions in sets and then linearize and deform them. And when I say deform, I mean that if you take a permutation solution on the basis of a vector space and you deform it by 2 cocycle scalars, this is also a solution. So you can deform them a little bit. are these set theoretic solutions useful in physics? I made the mistake of talking with physicists about this because, I want to know if the things I'm doing are really interesting to physicists, what they want us to do research about and that stuff. And they told me, yes, they are useful. We use them, specifically in classifying anyons and fusion categories, and we have a lot of theory in that. It is definitely useful. I don't want to sell my research field dishonestly, so I will also tell you in what fields they are not useful or less useful. They are less useful when you're looking for charge-conserving solutions, because these set theoretic solutions cannot be charge-conserving unless you're dealing with trivial cases. And to people working in quantum computing, where Yang-Baxter gates are a thing that is used, I am sorry to tell you that set theoretic Yang-Baxter gates never provide a universal set of gates, which is a set of computational gates that make you approximate any other quantum gate to any desired precision. I don't want to go into details, but just know that these things exist in quantum computing. They're just not as general as people would like them to be. So maybe a little bit less interesting in there. But they are very relevant in pure mathematics, as we shall see. First, because they all give representations of the braid group. So as you can imagine, the elementary crossing in the braid group, you can send it to the braiding map. And the Yang-Baxter equation is precisely one of the defining relations of the Artin braid group. So this is a representation. When are two representations equivalent? Also, I will not give you details about that, but I have a paper about this that you can go and see. Basically, there is this notion called Drinfeld twist by Kulish and Mudrov, and two such representations are isomorphic if and only if they are Drinfeld twists of each other. Drinfeld twist in a set theoretic sense, which is not necessarily the one you already know. It's quite a nice description. They are also very interesting in group theory. So you all know what an abelian group is. It's a group where AB equals BA for all A, B, and G. In other words, this diagram down here. You cross and you multiply. This is the same as just multiplying. We can generalize this and give axioms for a braided group, which is not the braid group, it's a braided group, it's another thing. And it's a group with two actions of the group on itself, one on the left, one on the right, satisfying this compatibility down here. If you unpack what this means, you get some axioms that will pop up later again. And graphically, it's some compatibility of the crossing with the multiplication and the unit. Well, the canonical flip is a braiding on the group if and only if the group is abelian. In some sense, this is the best braiding you can have. But every group has a braiding, which is this rack theoretic one. And we have many examples of braidings that are neither one nor the other. We have lots of non-trivial examples of braidings on groups. And at this point, you would expect me to say that, yes, every braiding on a group is indeed a solution to the set theoretic Yang-Baxter equation. What you may expect a little bit less is to know that every solution to the Yang-Baxter equation in set is universally and functorially associated with a braided group, which is called its structure group. This gives you an adjunction with the forgetful functor, so this is sort of a free construction. And it connects very closely solutions to the Yang-Baxter equation with braided groups. Why do we even study braided groups if all groups are braided? Because not all braidings are equally good. The rack braiding is in some way the worst one because every group has it. And the canonical flip is the best one because only abelian groups have it. So it's kind of a way of measuring how close to an abelian group our group is. Not all groups admit, for instance, an involutive braiding. Involutive meaning that if you do it twice, you get the identity. As you see this, the braids do not magically unknot when you do them twice, so this is not a property of all braidings. And not all groups admit an involutive braidings, and the groups that admit an involutive braiding are called the multiplicative group of braces, for reasons we will see, and there are conjectures on them, some of them not still open, and some of them are even quite big. A braided group can be investigated from the viewpoints of a sort of a ring theoretic, viewpoint. A skew brace is a nice structure which is just two groups on the same underlying set, and they are connected with each other by this compatibility down here. If this compatibility looks weird, just remember that this forces the two neutral elements to be the same for the two groups. The additive group isn't necessarily abelian. It's just a group that can very well be non-abelian. This definition was given by Guarnieri and Vendramin, and the reason why they gave this definition is because braided groups and skew braces are the same thing. And when I say the same thing, I mean there is really an isomorphism of categories between them. So in particular, every solution to the Yang-Baxter equation produces a braided group and hence a skew brace. So we have these two adjunctions over here, and these two things are basically the same thing. Okay, this was the wide picture on sets. Now let's talk about quivers a little bit. Let's do the quiver theoretic part of the story, which is if a group is a groupoid with one vertex, now let's study braided groupoids. If a set is a quiver with one vertex, now let's study solutions on quivers. Why this? Because we try to get ideas on partial solutions, and we try to compute solutions by globalizing partial things. This is actually not my own idea. This was an idea of Fabien Chouraqui, I think 10 years ago or such. Maybe a little bit less, maybe 4 years ago. Anyway, I was not really around in the research environment when she came up with this idea, but it's kind of an old idea. We're just developing the formalism right now to deal with this. The Yang-Baxter equation, as I said, can be defined in any monoidal category, so we studied in C equals quiv lambda. As I said at the beginning, this is a monoidal category. What is a quiver theoretic solution? It's a strong morphism from Q tensor Q to Q tensor Q. Now, since this is a set of paths of length 2, the solution is allowed to move the central vertex, but it's not allowed to move the first and the last one. So a solution will look like this. Takes a path into a path, moving the central vertex possibly, but it closes a square. And if you want to visualize the Yang-Baxter equation, this is a condition on length 3 paths, and the condition is roughly this one. You move the first two once, then the second two, and then the first two, and this must be the same as moving the second two first, then the first, and then the second. So the Yang-Baxter equation is a cube relation, which I find it very nice. And it has topological interpretations, as you can imagine, but we are not touching them today. One of the other reasons to study a quiver theoretic Yang-Baxter equation comes from physics again. Physicists like to study a thing called the dynamical Yang-Baxter equation for reasons they know. And a set theoretic version of the dynamical Yang-Baxter equation was given by Yoichi Shibugawa in 2005. And it involves the definition of a dynamical set. A dynamical set over lambda is a set with a transition map lambda times x to lambda. called phi. And the category of dynamical sets over lambda is monoidal again, with a proper notion of morphisms and tensor product that I will not give to you, because just want to keep it simple. But it's again a monoidal category, so we can define a Yang-Baxter equation again, and this is the dynamical Yang-Baxter equation. But this is not really something new, because as you can imagine, dynamical sets can be seen as quivers, just labeled quivers. When you have this set lambda, you can turn it into a set of vertices. You can turn the elements of X into a set of labels. And for every vertex lambda, small lambda, you have arrows going out of lambda, and these arrows are labeled by the elements of X. This set of arrows going out of a vertex, we call this the outgoing star, or the set of outgoing arrows. So basically, X labels the set of stars, and phi gives you the target map. This is a functor that sends dynamical sets into the category of quivers. It's a monoidal functor, and the essential image, as you can imagine, it's the sets of quivers where all the stars have same cardinality. This functor was given again by Matsumoto and Shimizu. And what we're going to do in the next slides is start from braided groupoids, define a quiver theoretic version of skew braces, define a dynamical version of skew braces, and say that the two things are roughly the same, which is not entirely trivial. Quiver theoretic versions of skew braces are nice because they have ideals and quotients, and they have nice geometrical interpretations as sort of a discrete version of a manifold with sort of a discrete tangent space at every point. You will see it in a moment, it's very nice. But dynamical skew braces are nicer to do computations, and they have a much nicer combinatorics. So we also need them, because whenever we want to plug all these things into a computer and do computations, the dynamical approach is much, much better. What is a groupoid? It's a category whose arrows are all invertible. But for us, it is a quiver with a quiver theoretic binary operation, which is only defined on the set of consecutive arrows. So it is a map, it's a morphism from G tensor G to G. It doesn't have a single neutral element, but it has a family of neutral elements, one loop on each vertex. And the inverse is a map that takes an arrow into its reversed, as you can see here. And then you have the associativity and the unitarity and all the rest. If you think about it for some minutes, you probably notice it by yourself. The underlying quiver of a groupoid is a disjoint union of connected components, and each connected component must be a complete graph, except a complete graph where the arrows have some multiplicity, which is the same for all pairs of vertices. So for instance, this one is a complete graph on 3 vertices of degree 1. This is a complete graph on 4 vertices of degree 2. All connected components are like this. Degrees may vary among different connected components, but they all look like this. So they're very easy quivers to describe. And what is a braided groupoid? It's the exact same thing as a braided group, except that everything is now partial. You just write down the exact same axioms. You just have to take into account the sources and the targets, which I'm not writing down here, but everything is consistent. Let's now define the quiver theoretic version of skew braces. This was given by Sheng, Tang, and Zhu in 2024 and was called skew braceoids, which is a little bit of, I mean, the name is already used for something else. Something else that is also probably connected to skew braceoids in the quiver theoretic sense. I have now an ongoing work with Isabel Martin-Lyons, Ilaria Colazzo, and Geoffrey Janssens about this. So maybe this is not the best choice, But on the other hand, people claim that Martin Lyons and Schumann's quivers were also not the best choice of a name in the first place. So yeah, we have two different things that are called the same name. I'm sorry. But in the rest of this talk, quivers will only mean quivers in the sense of Sheng, Tang, and Zhu. And they are groupoids with an additional group structure on each outgoing star. And these two structures, the groupoid and the bundle of group structures, they satisfy a compatibility which is exactly the same as the skew-brace compatibility, except that this is the group structure on the vertex target of A, and this is the group structure on the vertex source of A. They are different groups now, but it's the same thing. And the theorem is that skew-braceoids and braided groupoids are actually equivalent. Now, dynamical skew braces, just sometime later, I came up with this definition of quiver theoretic versions of skew braces working from the side of dynamical Yang-Baxter equations. And some months later, another colleague of mine came up with the same definition working with cycle sets. So it's really a definition that can be retrieved from multiple paths. And the notion of dynamical skew braces dates back to Matsumoto, and it's basically the following. It's a little bit complicated. You don't have to necessarily understand it immediately. I will have a picture later. But the idea is that you have a dynamical set, you have a group structure on the dynamical set, and then you have this mysterious family of left quasi-group structures indexed by lambda that satisfy two mysterious-looking equations. One of them is a dynamical version of the associativity when you reassociate two of these quasi-group structures, but you reassociate them taking into account that now they are different structures, so they move according to this map phi. And then you have the usual brace compatibility between the additive and the multiplicative structures. Such a dynamical skew brace is called zero symmetric if zero circle A is A for all circle operation. And the nice thing is that when you apply the functor I was talking about and read the dynamical set as a quiver, this family of left quasi-group structures, which is a bit hard to interpret, simply becomes a binary operation on the quiver. And if this dynamical skew brace is also zero symmetric, this is a groupoid operation. So this thing is sort of encoding a groupoid structure. You also have a purely group theoretic way of reading all this as some sort of families of subsets of the holomorph of a group. So you start from a group, you take the holomorph, which is the semi-direct product over here, and you can construct families of a certain sort. And these families that satisfy some properties will give you dynamical skew braces. This is a one-to-one correspondence. I don't want to delve into this, not in detail, because it's just complicated, but the reason why I'm presenting this interpretation too is because when you do computations with a computer, what you feed your computer with is this definition here, because there are some computer algebra systems that can work very well with groups and subsets of groups, semi-direct products, and the holomorph. So this is the formulation you usually use in that case. Let's give you just a big picture of what's going on. So a skew braceoid is a groupoid where on each outgoing star you have an additive group. Think to this as a sum of vectors in the tangent space of a manifold. In a dynamical skew brace, you have roughly the same thing, except that all these tangent vector spaces, tangent abelian groups, really, they all come from the same group. Now, what is not entirely trivial to show, you can see this paper from 2024, I think it's called On Dynamical Skew Braces, is that you can take any skew braceoid and parallelize it, sort of, and make it come from a zero-symmetric dynamical skew brace. You can do this on every connected component, and it works. So you can make all these group structures come from the same one in some way. And this connects these two worlds together. But dynamical skew braces are a little bit better than skew braceoids on something, because you immediately see that every group has a maximal zero-symmetric dynamical skew brace on it. Why this? Because, as I said, a dynamical skew brace is just a certain subset of the holomorph, and you can take the maximal subset that satisfies the defining properties. If you do this, you obtain what I call S0A, which is this maximal zero-symmetric dynamical skew brace. You don't necessarily have anything similar in the language of skew brace, or it's not immediately, at least. For instance, if you take the group Z modulo 3, the maximal dynamical skew brace on it is given by this quiver, and the maximal non-zero symmetric one is given by this quiver down here, but we're not interested in it right now. You see that this is not a groupoid, but what I call the left semi-loopoid at some points. Really no need to talk about that. For Z modulo 4, this universal dynamical skew brace looks like this. It has 4 components, one with 4 vertices, one with 2 vertices, and 2 with 1 vertex. Now, of course, the shape of the quiver is entirely determined by a string of integer invariants. So you have, for each S dividing the order of the group, how many connected components of each vertices you have. Of course, I would also need to know the multiplicity of the arrows in these connected components, but the fact is, number of vertices times the multiplicity equals the order of the group. So the multiplicity for the connected components with S vertices is going to be order of A over S. They can be determined from each other. This is nice because every finite group is now associated with a string of integers. A string of integers that is completely mysterious. We only know this relation of them. And it's also not very easy to compute because N1A is the number of skew braces on A, and how many skew braces with additive group A are there is an open problem, but maybe the other numbers are easier to compute and they can also give you a bound on the number of skew braces, which would be an interesting application. Example for Z modulo 3, N1 is 1 and N3 is 1. For Z modulo 4, these numbers are 1, 1, and 2 because there are 2 components with 1 vertex. For Z modulo 2 square, N4 is 50, N2 is 6, and N1 is 4. This has been computed with GAP, so I didn't do the computations by hand, and the computational complexity explodes very, very fastly, so very, very quickly. So it's very hard to do computations on that. I am concluding very, very soon, but let me tell you one last thing before I close. So the theory of groupoids is very old. If you're interested in some reading about some theory of groupoids, the entire oeuvre of Ronald Brown is out there. He wrote dozens and dozens of papers on groupoids, and they're all highly recommended, most of them from a topological viewpoint. If you're just interested in categorical similar products, you can check out my last preprint and also a former article by Meteri and Montoli on the semi-direct products on the categories of groupoids with fixed vertices. But when the theory was born, some people argued that the theory of groupoids is really not much more than just the theory of sets plus the theory of groups. Because what you can do is that you can decompose every connected groupoid as its set of vertices and any of its isotropy groups, because they're all isomorphic. And this is known from Brown already. And many people said, so you admitted yourself, your groupoid theory is just set theory times group theory. And while this is right, it's also kind of wrong in multiple ways. First, because there is no canonical way of decomposing a groupoid into sets times groups, because you need to find a wide coarse subgroupoid. Never mind what it is, but this operation cannot, if you know what it is, this operation cannot be done canonically in any possible way. So this is absolutely not an equivalence of categories. And second, while this is technically true for groupoids, that they can all be decomposed like this is not at all true for skew brazoids. So the theory of skew brazoids is indeed richer than the theory of groupoids. The thing is, whenever you take a groupoid, you can take the subgroupoids of loops, where you only take the loops. This is completely disconnected, and it's just a union of groups, the group of loops. And then you can take the quotient, because this one turns out to be a normal subgroupoid, so you can take a quotient. And this is a coarse subgroupoid, meaning that between any pair of vertices, you have at most one arrow. This is the thinnest groupoid you can think of. This is a short exact sequence that, by the way, splits, although not canonically. And the object on this side is a union of groups, and the object on this side is a coarse groupoid, which is essentially just a set, the set of vertices. When you try to do the same with skew brazoids, and you take the subgroupoid of loops, you will notice that the subgroupoid of loops, while being a normal subgroupoid, it is not an ideal. It is not stable under the braiding. Meaning that braided groupoids are not just a product of an object of the left-hand side type times an object of the right-hand side type. They are more complicated than this. This makes the entire theory so much more complicated for this, and also so much more interesting, because this is really not just the theory of skew braces times the theory of the objects on this side are called heaps. No need to know what they are. If you know what they are, good. So the theory of skew braces is not just the theory of heaps times the theory of skew braces. It's much more complicated than this. We know nothing about it. And if you want an easy counterexample, here it is. It's one of the components of the universal dynamical skew brace we have seen before. It's this component here. This component is not decomposable anymore. This is a simple skew brazoid, which is neither of one type nor the other. Neither a skew brace nor a coarse skew brazoid. So, well, by giving an insight on how complicated this theory can possibly be and how this theory can help possibly with the theory of skew braces, I will end my talk here. And thank you for your attention. And your questions are welcome.
Thank you for the nice introduction. Any questions or comments? Maybe I'll ask one question. So I'm not an expert in the Yang-Baxter equation side, but more I study skew braces. So these dynamical skew braces and like the quiver version, should I think of them as generalization of skew braces that are useful for studying Yang-Baxter equation?
They are generalization of skew braces, of course, like the one vertex situation is just skew braces. I think they might be useful to study the Yang-Baxter equation because of this. Because every finite group has a universal dynamical skew brace, or skew brazoid if you want, but not a universal skew brace automatically. So you can try to count, or at least give some sort of bound on the number of skew braces by using this relation and computing actually the higher numbers, which could possibly be easier to compute. I have no idea. But this is all combinatorially very complicated.
So
And
possibly,
also,
go ahead.
yeah, sorry. And possibly also partial structures can be used to define global structures by operations of globalization. But this is uncharted territory and it's an open project at the moment.
So potentially studying these dynamical skew braces would help understand structures of skew braces, possibly.
Potentially, yes. It's not just a generalization we do just because we like generalizations. There are a couple of motivations behind it. Of course, it's also a quite nice generalization if you ask me, but yeah.
Okay, thank you. I think we have a question in the audience.
Yes, please.
Thank you very much for your talk. So yes, I have a question about the skew braceoids. So a skew brace can be seen as a set with two different group structures compatible in some way. So here, skew braceoid, if I understand well, you have two groupoid structures which are compatible in some way, but one of the groupoid structures is just a group bundle. Am I right?
In some way, yes.
Yes.
Because you have a groupoid structure and a bundle of group structures, except that this is a bundle formed with a map that is not the source, that is not the source map.
So it
will end up being a bundle of group structures of outgoing arrows. It's a little bit more complicated.
So it is the additive structure, which is a
Yes.
group bundle, right? Could you imagine some kind of skew braceoid in which you have two groupoid structures, none of them is a group bundle?
This is of course an interesting question. I really think not, because this one is the most natural way and is the one that gives you the one-to-one correspondence. But your question could be connected to a higher categorical interpretation. Say, if you want to rewrite everything in terms of, I don't know, two categories or something, then something like two classical groupoid structures may arise in a higher context like that. I haven't seen specific motivations to formalize this in this higher language, but it could very well be.
Okay, thank you.
Any other questions or comments? If not, then let's thank the speaker again. Okay, thank you very much.
Thank you.